In the previous videos, we talked a little bit about statistical inference with confidence intervals. In this video, we're going to be talking about p-values. P-values are the most commonly reported measure of statistical significance. So they're used all the time in papers. You see them reported in almost every medical journal paper that you read, although that's changing a little bit in recent years. They're also used very frequently for decision making. For example, the FDA, Food and Drug Administration in the United States, uses them when evaluating whether effects are statistically significant for in the purposes of making decisions about drugs that are used in the United States. They are, however, incredibly controversial among statisticians. So I've linked here to one example of a listing of a large number of critiques of p-values that have been used by statisticians, and I think the primary reason for that is that p-values are one of the most misinterpreted statistics as well as one of the most widely used statistics, and so it brings down a lot of attention. Of course, not everyone thinks that p-values are awful. This is actually a screenshot of the blog that I write where I talked about how p-values and what's called hypothesis testing get a bad rap, but they can be useful if they're used in, I think, an appropriate way and are used in a way where the interpretation is correct. So what is a p-value? The basic idea at sort of a general level is suppose that there really is nothing going on. There's no relationship between the variables that you're performing a regression analysis on. How unusual is it to see the estimate that we got? And this is a little bit of a different question that you might think, it's not necessarily the question how likely or how unlikely it is that there's a relationship between the variables. It's actually just how unusual it is to see this estimate that we got if there was nothing going on at all. So we can define the approach to doing a p-value calculation in 3 steps. First, we have to define a hypothetical distribution for the data summary statistic when nothing is going on. We call this the null hypothesis and the null distribution. And the null hypothesis being the hypothesis that nothing is going on and the distribution corresponding to that hypothesis. And then we calculate the summary statistic with the data that we have, and we get what's called a test statistic. Then we compare what we calculated to our hypothetical distribution and see if the value is extreme or is surprising. And so we do that, we actually calculate the p-value itself. So we're going back to the Galton data for this example, and so in the Galton data we have the mid-parent height versus the child's height in a scatter plot, and then I've overlaid on top of this the least squares line fit through the data. So you can see that these data do seem to have a relationship, but we can hypothesize that there's actually no relationship between the two variables. And so beta hat 1 is the slope term relating the mid-parent height to the child's height. And so if that slope was equal to 0, in other words, if this scatter plot had no trend in it, it was just sort of flat, you would imagine that there was no relationship between the two variables. So our null hypothesis is going to be that B1 is equal to 0 exactly. So under the null hypothesis, we actually want to find the distribution of this statistic, beta hat 1, divided by the standard error of beta hat 1. And remember from the previous lecture that if we actually knew what the true value of B1 was, and we subtracted that off, this had a t distribution with n minus 2 degrees of freedom. So what we're doing here is we're saying hypothetically, suppose B1 is equal to 0 and we actually knew that. This is the distribution of what this statistic would look like. So then we can actually compare that statistic to this distribution and see if it looks like it's coming from a surprising place in that distribution. Then we might start to think that something actually is going on. So here's actually a plot of the null distribution in this case. So in this case there are 928 samples, and we use 2 of those samples to estimate or 2 of those degrees of freedom to estimate the parameters. And so then we can actually show what the distribution of the t distribution with 926 degrees of freedom is. And so you can see that it's sort of very narrow here, around 0. And so we can see then the actual value of the statistic that we get by calculating that t statistic, which was the estimate beta b1 hat divided by its standard error, or its estimated standard error. And we see it's all the way out here in the distribution. And so it seems kind of unlikely that if nothing was happening, we'd assume that the statistic we calculated would be drawn from this distribution, and it'd be pretty likely that it would come from this area near 0, but it actually turns out it's all the way out here, so it's actually kind of an unlikely result given that we have um, the null hypothesis or the hypothetical distribution that B1 is equal to 0. So how do we calculate these p-values in R? So again, we have this LM1 object. So this is the linear model that I used relating the child's height to the parent's height. Remember, R always calculates an intercept term plus a slope term for all of the variables you put on the right side of the tilde. And so here I've got the intercept term and the parent's height slope term. And I also get its standard error. And then R actually reports the t-value. So the t-value is the estimate divided by the standard error. And so we get a t-value here for the slope of 15.71. And then we get a p-value for that. So I'll show you in a minute what the p-value is, but in this case it's very, very small. This is a machine precision for R, 2 times 10 to the negative 16th. So it's saying that this p-value is as small as we can calculate given how well our computer can calculate small values. So just to show you exactly what the p-value calculation is, I'm going to show you a really simple simulated example. It's kind of hard to see with that t-distribution with 926 degrees of freedom. So suppose I generate some y values from a normal distribution and then some x values also from a normal distribution. And you can see that the way I've generated these two sets of values is totally independent, so there shouldn't be a relationship between them. So then I can fit a linear model like this, relating the y values to the x values, and look at a summary of that linear model. So now I get a standard or an estimate for the slope for the x values of 0.289 and a standard error of 0.389, which corresponds to a t statistic of 0.74 and a p-value that's 0.48. So that's actually quite a large value because we're not at all surprised to see a value of 0.289 with this big of a standard error if nothing was happening at all. And so here again, I'm showing you the distribution now of the t distribution with 8 degrees of freedom because we had 10 samples and we used 2 to estimate the parameters. And so this is the statistic that we have observed, and as you can see, it kind of lands right in the meat of the distribution, so it doesn't seem that unlikely. And the way that we calculate sort of unlikely or extreme is we actually take that statistic and we look how much probability density is over here to the right. So we basically look at the area under the curve to the right. Now, extreme could be in either direction. It could be positive or it could be negative. And so we actually calculate the area both to the right of the positive value of that variable or of that statistic. And then also we reflect that around 0 and we take the negative of that statistic and we actually calculate the area over to the left as well. So we say extreme in magnitude for the distribution. So this is extreme in magnitude but negative, and this is extreme in magnitude but positive, and so this area ends up being equal to the p-value that we calculate. So you can see that if our statistic lands sort of in the middle of the distribution, we're gonna average over most of the, we're gonna get most of the area under the curve. And since this is a distribution, we actually know that this area is equal to 1. And so if we say landed directly at 0, we'd get a p-value of 1. And if we got a statistic that was way, way out here, we would get a p-value that was much smaller since we only have this tiny bit of area out here on the edges of the curve. So p-values have a few specific properties, and they're really important to know when interpreting the results of these analyses. So the first is that suppose that we perform lots and lots and lots and lots of studies, and in each one there's absolutely no relationship between the x values and the y values, and in each one we calculate a p-value for the slope, and we made a histogram of those p-values, then you would see that they take equally likely any value from 0 to 1. They have this what's called a uniform distribution between 0 and 1. Now they're not exactly that because I only did 100 studies, but if I had done thousands and thousands, these bars would tend to level out towards this red line right here, which is the uniform distribution. So practically what that means is that if you choose any particular place where you say any p-value less than this is one that I would consider to be interesting, then whatever that cutoff is, alpha, say, alpha percent of the time, the p-value will be less than that because it's sort of uniformly distributed between 0 and 1. So if there's a bunch of data sets here, 100, where there's actually a signal, so in this case, the y values are generated such that there actually is a relationship to the x values plus some noise. We see that the p-values start to get, on average, a little bit smaller. So instead of being sort of just totally flat, they start to move over a little bit to the left. And an interesting property of p-values, so regardless of how big the sample size is, regardless of how many samples we draw, under the null hypothesis, they will always be uniformly distributed. The p-values will always be uniform. But if the alternative hypothesis is true, then the p-value depends not only on the signal, how big of a slope there is between the two variables, but also how big the sample size is. So in this case, we actually have the exact same signal in the data. In other words, the slope is still 0.2 times the x values plus normal noise. But in this case, I've created a sample size of 100 as opposed to a sample size of 20, and you can see that the p-values are much, much, much smaller. And so the p-value measures both the signal that you care about and the size of the data set. So if you've got two data sets of very different sizes and they both have p-values, they won't necessarily be comparable to each other. So p-values are used typically to make a decision about whether you think that there's really a relationship between the variables or not. And of course, there are definitely some statisticians who would disagree with the use of p-values for making these sorts of decisions, but they are really widely used and widely recognized as a solution, maybe not the best or the right solution depending on who you talk to. So the usual values that people report is if the p-value is less than 0.05, it's called statistically significant. If it's less than 0.01, it's strongly significant, and maybe very, very, very significant if it's less than 0.001, and so forth. So in general, 0.05 is the value that people use for statistical significance. This was a totally arbitrary value made up by a statistician who was asked to come up with some value for significant, and he said, I think 1 out of 20 mistakes is a reasonable number of mistakes to make. But in modern analyses, this may not be a small enough value, especially if you're testing a lot of different slopes, a lot of different relationships. In most modern analyses, people generally report both the confidence interval that we talked about before, so you get an idea of the slope term itself and whether that slope term is scientifically or has business meaning, as well as the sort of the p-value. This is less true if many, many hypotheses are tested. If there are lots and lots and lots of hypotheses tested, often the confidence intervals are suppressed and just the p-values are reported for identifying which relationships were statistically significant. So here's how you would interpret or write up the results of this linear model. So if you have a linear model relating child's height to mid-parent's height, you can get the coefficient matrix, and so you get the estimate and the standard error for the intercept and for the slope, and it has a t-value and a p-value. And so you remember you would report a 1-inch increase in parental height is associated with a 0.77-inch increase in child's height with a 95% confidence interval. In this case, you might say something like this difference was statistically significant, or you might even say strongly statistically significant. And people, rather than reporting p equals this really very small number, they sometimes censor the p-value, so they say p is less than 0.001, where they choose a small enough number here that indicates how small the p-value was without having to write out in scientific notation the very, very tiny values, which might not necessarily be totally interpretable. So you have to be a little bit careful about how you interpret p-values and how you use p-values. Like I said, there are a lot of statisticians who are somewhat nervous about the way p-values are used, and I think maybe rightly so. So here's an example that's kind of a funny example. So you can imagine someone saying, well, jelly beans, coming up with a hypothesis that jelly beans cause acne. So scientists are going to investigate it, and so they first just test and see if there's a relationship between jelly beans and acne, and the p-value is greater than 0.05. And then they decide to actually try a bunch of different color jelly beans, and in each case the p-value is greater than 0.05, and they do this 20 times. But remember, the p-values, if there's absolutely no relationship, are distributed uniformly. So that means about once out of every 20 times, about 1 out of every 20 times, it'll be less than 0.05, even if nothing is going on. So when they get to green jelly beans, they actually determine that the p-value is statistically significant, and they report this value in the news. And so this is probably one of the reasons for a lot of false positives in the news, and it's something to keep in mind, that the p-value itself on its own probably isn't super informative, but it can be a very helpful tool for decision making.